Hi, thanks for joining me. Today I'm going to be going over problem 5 from the Imperial College Maths competition. As always, I'll leave a link in the description below with details of the competition. This is the problem I'm going to be tackling today. We want to find all composite positive integers m, such that whenever a and b are natural numbers which divide m, such that a times b equals m, then a plus b is a power of 2. So we want to find all positive composite natural numbers m, such that if a and b divide n for any two factors of m, such that ab equals m, then a plus b is always a power of 2. Okay, so if you're going to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so there are in fact a few different solutions to this problem. The one I'm going to present to you, in my opinion, is the easiest to follow, but there are other solutions as well, and you can check them out in the link in the description below. But yeah, let's get stuck into this one. We're going to suppose we have a positive natural number m with the property, so m is composite, and also whenever you have two natural numbers a and b which multiply to give me m, we have that a plus b is also a power of 2. So firstly, m times 1 equals m, so certainly m plus 1 must be a power of 2. So that's sort of setting a equals 1 and b equals m. So then we have that m plus 1 is a power of 2, so let's call it 2 to the k for some k. But also, because m is composite, certainly it has some prime divisors. So without loss of generality, let p be its smallest prime divisor. So let p be the smallest prime divisor of m. So then that means we can write m equals p times x for some natural number x. But now notice that p must be less than or equal to x, because if x was less than p, then x would certainly have some prime factors, either less than or equal to x, and then that would contradict the fact that p is the smallest prime factor. So we have that p is less than or equal to x, but also by this property, we have that p plus x must be a power of 2. So p plus x equals, say, 2 to the l for some number l. Now what else do we know? We want to try and build a relationship between L and K. Well, firstly, we know we can write this first equation, m plus 1, as just px plus 1. Now, what do we know? 2 to the L is equal to p plus x, but we know that p is certainly less than or equal to x, so this thing here is less than or equal to x plus x, which is just 2x. But now we know that the smallest prime number is 2, and so any prime number is at least 2. So this thing here is certainly less than or equal to p times x, because any prime p is bigger than or equal to 2. But obviously this thing here is strictly less than px plus 1. But px plus 1 is just 2 to the k. Okay, so we get that 2 to the l is strictly less than 2 to the k, which means that l is strictly less than k. Okay, so we've derived this inequality. Let me wipe the whiteboard clean, and then we'll continue. Okay, so we've just derived an inequality, L is strictly less than K. What I want to firstly do is derive another quick inequality. We have that 2 to the L is equal to P plus X. But remember, we know that X is bigger than or equal to P, so this thing here is bigger than or equal to P plus P, which is just 2P. But we know the smallest prime number P is 2, so this thing here must be bigger than or equal to 2 times 2, which is 4. So then that tells us that L must be at least 2, because obviously 2 squared is 4. Okay, so that gives us another inequality. L is at least 2. Okay, now what we want to do is try and derive another inequality. And it's not particularly clear how we derive it at first, but if we have a bit of a play around, if we look at this top inequality here, what I'm firstly going to do is add p squared to both sides. So we get p squared plus px plus 1 equals 2 to the k. And I guess one thing I should have said is this, plus p squared, of course. Now, of course, this doesn't change any of the solutions, because if I have this equation here and I want to try and work out solutions, of course I could just cancel out p squared from both sides. And in fact, I know this equation has a solution in terms of p because of sort of the construction of this equation here. Anyway, now what I want to do is sort of factor this left-hand side, take out a p from here, and then write it as p times p plus x. So this thing becomes this thing, plus 1 equals 2 to the k plus p squared. But of course, p plus x is just 2 to the l. So I get p times 2 to the l plus 1 equals 2k plus p squared. Okay, so let me just bring this equation up here. and we'll have a quadratic in terms of p, which we know has a real solution, so then we can say something about the discriminant. So let's just bring everything onto one side. So we get p squared minus 2 to the lp, then plus 2 to the k minus 1 equals 0. So that's our quadratic we have in terms of p, and we know this has a real solution, so the discriminant has to be at least 0. So what is the discriminant? It's b squared minus 4ac, so minus 2 to the l all squared, minus 4 times 1 times 2 to the k minus 1, and that has to be bigger than or equal to 0. This thing here is just 2 to the 2l, minus, now 4 we can write as 2 squared, so when we expand the brackets we get 2 to the k plus 2, and then minus 4 times minus 1 is plus 4. So then we get that 2 to the 2l is greater than or equal to 2 to the k plus 2 plus 4. That's not right. 2 to the k plus 2, sorry, is less than or equal to 2 to the 2l plus 4. Okay, so we have this inequality here, and now here's where the sort of trick comes in. We know that L is at least 2. So, and we know the left-hand side here is a power of 2. So we certainly know we can bound it by a power of 2. So if this thing here isn't a power of 2, then we can bring this down to the next biggest power of 2. Sort of like if I know that I have a natural number t, and I know that t is, say, less than pi, then I know that t is certainly less than or equal to 3, because I know that t is a natural number, and t is less than 3.14 or something. So I not only know that t is less than pi, but I can make it a bit better and know that t is less than or equal to 3. It's a similar thing going on here, except with powers of 2. I know the left-hand side is a power of 2, and it's bounded by this thing here, but certainly because it's a power of 2, I might be able to bring it down a bit further to the next next biggest power of 2 that's below this thing here. And I know this thing here isn't a power of 2. Why is that? Because L is at least 2. So 2 to the 2L is 2 to the 4, which is 16. So any power of 2 which is bigger than 2 to the 4, certainly when I add 4, I'm not going to get another power of 2. So what's the smallest power of 2? Oh, sorry, the biggest power of 2 less than or equal to this thing here? Well, it's going to be 2 to the 2L. So then I can conclude that 2 to the k plus 2 is less than or equal to 2 to the 2L. And then that, of course, gives me that k plus 2 is less than or equal to 2L. So in other words, k is less than or equal to 2L minus 2. Okay, so that's another inequality derived, and we're one step closer to solving this problem. Okay, so I've just gone back to the equation I had here, this sort of quadratic in terms of p. Now what I want to do is bring 2 to the lp on one side by itself. So that, of course, just equals p squared plus 2 to the k minus 1. Now what I want to do is divide through by 2 to the l, sorry. So p is equal to p squared minus 1 over 2 to the l plus 2 to the k minus l. Because obviously 2 to the k over 2 to the l is just 2 to the k minus l. Now remember at the start we derived that k is bigger than l, so certainly k minus l is positive. So in particular, not only is this a power of 2, but it's an integer. Or I guess not only is it an integer, it's a power of 2, but all we need is that this thing here is an integer. And we know p is an integer, so it follows that this thing here must be an integer. So it follows that 2 to the l divides p squared minus 1. Now firstly, what does this tell us? It tells us that p certainly must be odd, because if p was even, we'd have p squared minus 1 being 3, and we know that 2 to the l is at least 4, because l is bigger than or equal to 2. So we have some number bigger than or equal to 4 divides 3, which doesn't make any sense. So p certainly must be odd, okay? And we can in fact write this as 2 to the l divides p plus 1, p minus 1. Okay, so just completing the square. Oh, sorry, the difference of two squares, I should say. So 2 to the l divides this thing here. But now remember, we just said that p is odd. So that means that p plus 1 and p minus 1 are both even, but in particular, their greatest common divisor is 2. So 2 divides one of these things, and the rest divides the other thing completely. Okay, so so case 1, we have that 2 divides p minus 1, and then 2 to the l minus 1 divides p plus 1. And then case 2 is the exact same thing, except we swap that minus for a plus, and then that plus there for a minus. Okay, what we're going to do is consider these two cases separately, and then we'll be almost done in solving the problem. Okay, so let's look at case 1 first, where 2 to the l minus 1 divides p minus 1, and 2 divides p plus 1. But we only really need this piece of information here, and what I'm going to derive is a contradiction. So this actually can't exist. So 2 to the l divides p minus 1, so certainly then 2 to the l minus 1 must be less than or equal to p minus 1. but in particular it's strictly less than p. But remember at the start we had that p plus x equals 2 to the L. Remember x is bigger than or equal to p, so this thing here is bigger than or equal to 2p, so we get that 2 to the L is bigger than or equal to 2p. Not 2 to the p, just 2p. But then if we look at this inequality here, we have that 2 to the L minus 1 is strictly less than p, so certainly that means that 2 to the L is less than 2p, and we have a contradiction, because 2 to the L can't be bigger than or equal to 2p, and simultaneously be less than 2p. Okay, so this situation doesn't exist, so the only other case is that 2 to the L minus 1 divides p plus 1. Let me clean the whiteboard and we'll look at that case. And finally, let's consider the last case. So 2 to the L minus 1 divides p plus 1. So like before, what we just derived in case 1, we have that p is certainly less than or equal to 2 to the L minus 1. But because 2 to the L minus 1 divides p plus 1, it must be that 2 to the L minus 1 is also less than or equal to p plus 1. And because, of course, 2 to the L minus 1 is an integer, either it equals p or it equals p plus 1. But if it was p, then we wouldn't have 2 to the L minus 1 divides p plus 1. So it must be that 2 to the L minus 1 equals p plus 1. So then that we have that p is equal to 2 to the L minus 1 minus 1. But remember, p plus x equals 2 to the L. So p plus x is just 2 to the L minus 1 minus 1 plus x, and that equals 2 to the L. So we get that x is equal to 2 to the L minus 2 to the L minus 1 plus 1. But then this thing here, just sort of factoring out a 2 to the L minus 1, this thing here is just 2 to the L minus 1. So this is just 2 to the L minus 1 plus 1. Now we have what p and x are in terms of 2 to the L minus 1, and we can then derive an equality between L and k, because we know that px equals k. Px equals 2 to the k. So px equals m, and we know that m plus 1 equals 2 to the k. So px plus 1 equals 2 to the k, remember. But what's p times x? Well, it's 2 to the L minus 1 times 2 to the L minus 1 plus 1, so the difference of two squares. So this thing here is equal to 2 to the L minus 1 squared minus 1 squared, but then of course this plus 1 here, which cancels nicely with that. So we get that 2 to the k is equal to 2 to the L minus 1 all squared. So from that we can deduce that k is equal to 2 L minus 1, or 2L minus 2. Okay, let me clean up the whiteboard and we'll continue. Okay, so we've just derived that k is equal to 2 to the L minus, 2 times L minus 1, but in particular k is even. Now we have that px plus 1 equals 2 to the k, so obviously p times x equals 2 to the k minus 1. Now I claim that 2 to the k is congruent to 1 mod 3, and that's not too difficult to see. This thing here, 2 to the k, is of course just 3 minus 1 all raised to the k. But then if I think of the binomial expansion of this thing here, it's just going to be minus 1 to the k when I look at it mod 3, because every other term is going to divide 3. Going to be a multiple of 3. But of course, because k is even, minus 1 to the k is just 1. So this thing here is just congruent to 1 mod 3. Okay, so 2 to the k is congruent to 1 mod 3. So 2 to the k minus 1 is congruent to 0 mod 3. So that of course means that the 3 divides this right hand side. But because the left hand side equals the right hand side, it must be that 3 also divides the left hand side. Now, we know that p is certainly an odd prime from the argument we had before. So p is at least 3. But I claim that p has to be 3, because if p wasn't 3, then 3 would have to divide x, because remember 3 divides this left hand side, and if p is bigger than 3, because p is prime, it certainly won't divide 3, so then it follows that 3 must divide x. But then of course that means that we found a smaller prime factor of this left hand side, which is smaller than p, but then that contradicts the fact that p was the smallest prime factor of m. So it follows that p must equal 3. Okay, and now from this we can work out what x is, because we know that p times x, which is just 3x, equals 2 to the k minus 1, but that's just 2 to the 2l minus 1 minus 1, which is just 2 to the l squared times 2 to the minus 2. Okay, so just expanding this out is 2 to the 2l, which is 2 to the l all squared, times 2 to the minus 2, which is this thing here, minus 1. But what's 2 to the l squared? Remember, 2 to the l is just p plus x. So this thing here is just 3 plus x all squared times a quarter minus 1. So we can rearrange this. So adding 1 to both sides and then multiplying by 4. Let me bring it up here. So you get that, what was this again? 3x. 3x plus 1 times by 4 is equal to 3 plus x all squared. Okay, now this is just a quadratic in terms of x, and we're almost done. So this thing here is just 12x plus 4, and then that equals 9 plus 6x plus x squared. So bringing everything onto one side, we get that x squared minus 6x plus 5 equals 0. And this, of course, has the x minus 5, x minus 1 equals 0. And then the only solutions to this are 5 and 1, obviously. But remember, x is at least p, and p is 3, so this solution we don't consider. So it follows that x must be 5. Okay, so if there is a solution to our big problem, then the only possibility is p equals 3 and x equals 5. So all we have left to do is just check that that works. So in other words, if we have m, which we know equals px, which is 3 times 5, which is 15. Now we just have to check that m here has the properties that we want. So 15, when I do 15 plus 1, is that a power of 2? Yes, that's 16, that's great. And what are the only other factors of 15? Well, it's just 3 and 5. And 3 times 5 equals 15, and 3 plus 5 equals 8, which is a power of 2. So m equals 15 is one of these numbers, and in fact, it's the only such number, and that's the problem solved. Anyway, I hope you have enjoyed this video. I hope you have enjoyed this video. If you are new here, please do consider checking out some of my other videos as well. That's all for today. I will catch you in the next one. Have a great day.